Those of us that have seen trigonometric functions before, you're probably thinking, okay, I don't remember them being of arc length, right? You always talked about like sine of theta, cosine of theta, and well, yeah, we're gonna get there, and that's where this video comes into play because we can talk about trigonometric functions in terms of angles and not arc length, okay? But we need to relate the two first, okay? So remember that we have that arc length formula, S is equal to R theta, from our very first section where we looked at angles and stuff, right? And so in this video, okay, or in this section, right, we're using T instead of S, tomato, tomato, we're using T instead of S. Fine, fine. But now remember that for this unit, right, we're also working on the unit circle only, okay? Only, okay? When we work with the unit circle, what is the value of R? Well, it's called unit circle, right? That means R is 1. What's our equation become then? Oh, well, we get T is equal to 1 times theta, or T is equal to theta. And now we just have to remind ourselves, what is theta exactly? Okay, so T, we were using arc length, to represent arc length, rather. And theta, in this arc length formula, that was the measure of our central angle. Okay, so the takeaway is precisely this. Okay, when we're on the unit circle, if we're working with trigonometric functions, if it doesn't matter if we're talking about the trigonometric functions in terms of their arc length or central angle, they are the same. Okay, and so that just leads to the same old definitions, and this is literally copied and pasted from the first video in this series, where I just put T theta instead of T. Okay, the same definitions apply. Okay, the only difference is that theta is our central angle, and so just remember as a visual that central angle. If we have a quick little drawing here, we have an angle like this. This would be our arc length T. This is R, and then if I zoom in here, this central angle would be would be the angle from the positive x-axis. Okay, so there we go. Okay. Now, the upshot of all this is we don't have to be given an arc length. We don't have to worry about it. We can just work with a central angle. Okay, and this can allow us to find some very nice points and make some other nice conclusions from all this. Okay, for this first example, what point on the unit circle corresponds to a central angle of pi over 6? This one I'm actually going to sidestep, and I'm going to have you go to your ebook, or I'm going to say book or e-book, okay, and look at pages 465 to 466. It develops this theory nicely, okay? We can talk about it in different ways, but this pi over 6 degree, or pi over 6 radians is 30 degrees. So if you think about it, here's our unit circle, and we're interested in this point xy, okay? And we know that this angle down here is 30 degrees, right? What are the x and y coordinates corresponding to that? These pages go through and develop that nicely. What comes out of it is that x is square root of 3 over 2. I know, square roots, well, yeah, that's interesting. And then y is 1/2, okay? Some of you who have seen some trigonometry before might have different, patterns of recognizing all this with, and that's fine. But nevertheless, these are our x values, or x and y values corresponding to pi over 6, okay? Now this next one I will actually go ahead and do because it's actually a little bit more interesting. So what point on this unit circle corresponds to a central angle of pi over 4? Okay, well, we know that this up here is pi over 2 and this is 0, right? And pi over 4 would be exactly halfway between. Okay, so this is, our central angle pi over 4. We want to know what p of x, y are, right? All right, so to to figure out the x and y coordinates here, we note that pi over 4 is exactly half of pi over 2, right? So it's exactly half. It would kind of bisect, divide it into two equal parts, the first quadrant, okay? And so that would mean that if we kind of imagine this line here, okay, this line is the y equals x line, that exactly bisects that quadrant, or actually the first and third quadrants. But then in this case, you'll notice that y and x are exactly the same. So if I think about the unit circle equation, x squared plus y squared is equal to 1, right? And I know that y is exactly x. I can write it as x squared plus x squared is equal to 1, okay? And then, so I get 2x squared is equal to 1x squared. I'm just going through with the algebra, okay? And then x is plus and minus. Again, whenever you square it, you have to include the plus or minus. 1 over 2. Since I'm in the first quadrant, though, I'm only going to use the positive component because x can only be positive there. Okay, and if I simplify this down, this would be 1 over square root of 2, and then rationalizing, I'd get square root of 2 over 2. But nevertheless, I found what x is, and then this is exactly y, because again, y is equal to x when I'm at pi over 4. Okay, so 4 pi over 4 is equal to theta, this measure of the central angle. Then we have xy is equal to square root of 2 over 2, square root of 2 over 2, okay? And so that's really nice. And now if I put this information together along with what I know from above here, okay, so this first one, I'm going to say that this has a central angle of pi over 4, which is 45 degrees, okay? And the point here, this point is square root of 2 over 2, square root of 2 over 2, okay? This other one that we looked at was pi over 6, which is also known as 30 degrees. And for that angle, it was square root of 3 over 2 and 1/2, okay? Now, the other angle that you really need to know in the first quadrant is pi over 3, which is 60 degrees, okay? You can go through similar work that is done in the book for 30 degrees and find that this point as a coordinate is 1/2 and then square root of 3 over 2. Okay, now in our classwork so I did this for the first quadrant. Okay, you will have to do this for the second, third, and fourth quadrants, and really all you have to do is use reflections. Okay, I'm going to say use reflections. So imagine that if we reflected this over into the second quadrant, right? We move it over here. Well, in that case, all the the y values aren't going to change where they are vertically. All the x values just become negatives. Okay, so we'll work through that in class. Okay, but once we get this whole thing complete, what I'm going to say is I don't like the word memorize, but I think in this case it will benefit you immensely. But I'm going to say memorize the unit circle. Let me actually just add unit circle. Okay, so that is angles and coordinates. Okay, that will help you immensely. Okay, so now let's put some of this to work. Okay, we'll do a couple examples and then the last one is kind of a twist. Okay, note that, I guess before I go on, these are nice multiples. I guess they're 30, 45, 60. They're kind of nice angles. There can be wonky angles too, but we just won't be able to find their coordinates in a nice clean form. Okay, and that's fine. All right, first example says determine the point in the unit circle corresponding to 3 pi over 4. Okay, so now this is where I need a quick little sketch. Unit circle, okay. 3 pi over 4 would be 3/4 pi, right? So that's over here. So this would be my measure of angle theta, okay. And it says I need to determine the point, so I need the x and y point over here. So now this is where I recognize, okay, this point is a reflection of some point over here, and I notice that it would be a reflection of, let's see, so, okay, 3 pi over 4, that looks like it cuts quadrant 2 precisely in half, so it would be a reflection of pi over 4, okay? So this is negative, or sorry, positive square root of 2 over 2, and square root of 2 over 2 for a coordinate, okay? And now when I reflect it across the y-axis, right? The y-axis means, or y-axis reflection, let me write that again. Undo that. A y-axis reflection means that the y-coordinate stays the same, but then the x-coordinate would change to its opposite sign. Okay, so there I go. I have the point. Okay. So that one was easy, and that's sort of what you're going to do in the group work to complete the unit circle. Okay. Now, second example here is a little different, right? It says evaluate the 6 trig functions for this angle without a calculator. Okay, well, let's get a little sketch going. Okay, so 7 pi over 3. Oh boy. Well, I know that this is, let's see, if I just do the division, that's like 2.33 repeating pi. So that's like 2 pi, so 2 pi plus 0.33 pi, right? Okay. Or 2 pi plus pi over 3. Okay, fine. But now this is, I wrote it in this form just so I could understand, okay, so I do one complete revolution, right? And then I go pi over 3 more. Okay, so this would be 7 pi over 3. Okay, which is coterminal with pi over 3. And I know that pi over 3 has coordinates 1/2 square root of 3 over 2. Okay, that was one of the nice angles above, or nice coordinates above. Okay, so that'll enable me to do my work a lot quicker. Okay, but the trick here was to, or I don't say trick, but the insight that I had is I had to recognize that this angle had to be broken down into a different form. Okay, so if I look at this case, so if I do like sine of 7 pi over 3, okay, mathematically this is actually equal to sine of pi over 3 because they are coterminal angles. Okay, and remember, so the angles are distinct themselves, but they do end at the same place on the unit circle. So that's why I can claim equality. Okay, so that's an important piece to recognize. But nevertheless, sine is just the y-coordinate, square root of 3 over 2. Cosine, 7 pi over 3, would be the y-coordinate, or x-coordinate, so 1/2. And then tangent of 7 pi over 3 would equal square root of 3 over 2 divided by 1/2, which is just square root of 3. Okay, and then with that I can form my reciprocal functions. 7 pi over 3, secant 7 pi over 3, and cotangent 7 pi over 3. Okay, so this one I get 2 over square root of 3, which is fine for me. Connect math will want you to go further. 2 square root of 3 over 3 if you rationalize it. Secant is going to be 2, the reciprocal of 1/2, and then cotangent is going to be 1 over square root of 3. Again, fine for me. Connect math will want you to write it as square root of 3 over 3. Okay. Last example. Okay. It says, what point on the unit circle corresponds to the central angle of 5 pi over 7? Okay. Unit circle, 5 pi over 7. Okay, so I know it's not quite, so this is pi, and this is pi over 2 up here. I know it's more than pi over 2, but not quite pi, so it's somewhere over here. Okay, that's going to be my central angle. And I want to know what this point is. Okay, so keep in mind that since it's in quadrant 2, x is going to be negative and y is going to be positive. okay? Just something to keep in mind. But nevertheless, how do I find the x and y coordinate? Well, on the unit circle, remember that sine of theta is equal to our y coordinate and cosine of theta is equal to our x coordinate. So all I have to do is say that my point of interest, P of xy, should be equal to, as a point, cosine of 5 pi over 7, comma, sine of 5 pi over 7. And if I do this, I get approximately negative 0.62, 0.78. Now, sometimes when students are doing this, they don't get these numbers and like, what is going on? Like, I'm doing this a million times and I'm not getting these numbers. Okay, pay attention to what mode your calculator is in. Okay, here we have to be in radians, right? Because 5 pi over 7 is in radians. Sure, you could convert it to degrees, fine, whatever. But if you need to, your calculator might say like DEG, okay? If you need to change it to radians, which would be RAD typically, there's a button on your calculator typically that says DRG. So that's a button. Press that, and then you can, change it from degrees to radians. All right. So this video is meant to just connect, I guess, first allow us to say, instead of working with the arc length definition of the trig functions, we can work with an angle, the central angle on the unit circle. Okay, and then with that, our trig definitions stay the same, and then we just work through some examples related to that. All right, be ready to do classwork where we complete the unit circle, and we will use that over and over and over. Okay, so commit that to memory as much as you can.